Hi all, this is another video in my series on computer systems. In this video, we will be continuing our discussion of representing numbers. That's module 1 of the series. And in this video, we will talk about an introduction to how floating point numbers work. To start out, we'll take a look at what fractional binary numbers actually look like and how we can figure out the values of them. Then we'll talk about the ITripleE floating point standard and go through some examples and properties. So what are we looking at when we look at this binary number, 1011.101? Well, if we break it down, we find out that it works much the same as a decimal point in a regular decimal number representation. All right, so in this case, we're going to call it a binary point because, well, we're dealing with binary. But what this evaluates to is we've got our normal method of figuring out how much a binary value evaluates to on the left side of the binary point. So 1011, we've got a weight of 1 in the 2 to the 0 place, so that's 1. We've got a weight of 1 in the 2 to the 1's place, so now we're up to a total weight of 3. We've got a 0 in the 2 squared place, so we're still at 3, and we've got a 1 in the 2 to the 3rd place, so that adds 8, and we have a total of 11. But what do we do to the right of the binary point? Well, we find out that this works, again, sort of just like decimal. So in a decimal representation, this first 1 to the right of the binary point would have a weight of 1/10. Then the next would be 1/100th. The next would be 1/1000th. In this case, since we're dealing with binary, we basically just do the same thing. The weight of the first digit to the right of the binary point is worth 1 over 2 to the 1, or 1/2. The next one is worth 1 over 2 squared. The next one, 1 over 2 to the 3rd. So when we add all that up, we end up with 1/2 for that first one. We don't have any weight in the 1 over 2 squared place. And the 1 over 2 cubed place has a 1. So we've got 4/8 plus 1/8. This entire thing will evaluate, when we convert it to decimal, this is going to be 11 5/8. So let's take a look graphically at how that all works on the next slide. So when we break this down, we find out that it works very similarly to integers. We just have to add that binary point and some stuff to the right of it and sort of figure out how do we deal with that. Well, remember that we had our places. We had our I equals 0 place, our I equals 1 place, our I equals 2 place, and that indicates the exponent that we put on the base when we're figuring out how much the weight is worth. So for the 0 place, it's 2 to the 0, so that's worth 1. The 1 place, 2 to the 1 was worth 2, 2 squared is worth 4, and etc., all the way up to the most significant bit of our representation, and we're going to refer to that as I in this case. Now, as we move to the right of the binary point, well, we just keep counting down, right? So it's going to go b sub -1, b sub -2, sub -3. And so we're actually doing the same thing. When we attach that weight, a 2 to the -1 is worth 1/2. 2 to the -2 is worth 1/4. 2 to the -3 is worth 1/8. And that's just based on how exponents work, right? So we do the same thing. We find out what is the value in that place. We multiply that by the weight and add it into our total. And this goes all the way down to the furthest bit that we have to the right of the binary point, we're going to refer to with a -j. So bits to the right of the binary point just represent fractional powers of 2. Again, just as with decimal, they represent fractional powers of 10. With binary, it's a base 2 system, so we're talking about fractional powers of 2. So the way that we would mathematically represent a rational number as opposed to an integer is with another summation, right? We're going to go from k equals -j, right? So -j, that's our furthest to the right of the binary point. We'll just count all the way up from that negative value all the way up to I, which is our most significant bit to the left of the binary point. For each iteration, we add b sub k, so the value of the bit in that place times 2 to the k. So really, when you break it all down mathematically, this is almost exactly the same as dealing with an integer. We're just going to have some negative exponents thrown into the mix. So to quickly work our way through some examples, if we've got 101.11, right, then we just add things up just like we would have before, right? Let's walk our way through that summation from the last slide. The 1 that's to the far right, that's to the right of the binary point by 2, so that's worth 1 over 2 squared, or 1/4, plus 1/2, which is 2/4. We get 3/4, right? And then the 101 is just 1 plus 0 plus 4, so that ends up at 5 3/4. So this just works that way every single time, so you can work your way through why 10.111 evaluates to 2 7/8, 1.0111 evaluates to 1 7/16. It always works that way. So some observations we can make is we can divide by 2 by shifting to the right, just as we talked about in the last video. We can multiply by 2 by shifting left, so that's a handy little trick to have. And something that we want to note is that numbers of the form 0, binary point, and then a bunch of ones, right? So any number that has a 0, then the binary point, and then everything to the right of the binary point, for however big our representation is, if it's a bunch of ones, it's the value that can be represented with that number of bits that's just below 1.0. All right, so 1/2 plus 1/4 plus 1/8 plus etc. 1 over 2 to the I. We're going to approach 1, but we're never actually going to get there. So 1 is basically our limit at that. We'll get as close to possible as 1, but we never actually reach it until we roll over and have a 1 to the left of the binary point. Now, the notation we use for this, because depending on the representation size, these can actually evaluate to different values, right? The more bits I have, the closer to 1 I can get, because the more weight I can add in and get closer and closer to that limit of 1.0. So we use the notation 1.0 minus epsilon. And epsilon, as it so often does in mathematics, we're just representing a very small value. But again, because depending on how many bits we have to the right of the binary point, we have to use a variable because that can change. If I only have 1 bit to the right of the binary point, I can actually only get to 1/2. That's as much as I have room to represent. If I have 2 bits, I can get to 3/4. If I have 3 bits, I can get to 7/8, etc., etc., etc. So when we use this notation, we're kind of just indicating 1.0 minus whatever the small value is between 1 and all that weight in the binary point. That's what we're talking about. And we use that again when we have nothing but positive weight, nothing but 1s to the right of the binary point, to indicate that this is the form of the binary number that we're dealing with. So it's great that we know how that works, but there are a couple of limitations that we have to keep in mind, and this is actually kind of what gives rise to the whole idea of the floating point standard. First of all, we can only exactly represent numbers that have the form x over 2 to the k. Other rational numbers are going to have repeating bit patterns. Okay, so 1/3 will be 1, 0, 1, 0, 1, etc. It's just going to be 0 1s forever, right? And we've seen this with things like in decimal, when you talk about 2/3 and 1/3, same kind of thing. They have repeating bit patterns. That'll happen in binary too. 1/5 will be 0, 0, 1, 1 repeated. 1/10 will be 0, 0, 0, 1, 1, 0, 0, 1, 1. And eventually the 0, 0, 1, 1s repeat forever again. So that's one problem we have. Now, how do we go about representing those things? The second limitation is that just one setting of a binary point within the W bits, right? We're talking about a computer system, so all I've got is a word size. If I'm dealing with a 32-bit word, I've only got one place where I can put a binary point. I cannot mess around and do like different binary points in different places or something like that. I've just got one binary point to work with somewhere within those bits. Now that limits my range of numbers. If it's way up toward the most significant bits, then I can do a whole bunch of very small values, but I can't do many larger values. If I have it further off to the lower order bits, I can have pretty large values, but I can have a very limited range of small values. So how do we take care of this problem? How do we give ourselves more opportunities for representing larger ranges of numbers with a limited word size to work with? Well, enter the ITripleE floating point standard, which we'll go ahead and define and kind of show you how it works with the next few slides. So the ITripleE floating point standard was established in 1985 as a uniform standard for floating point arithmetic, and it's actually ITripleE standard 754 if you want to go Google that and take a look at the standard itself. But before that, there were a whole lot of different idiosyncratic formats. We didn't have a standard, right? We didn't have a standard way that these things were represented, and that causes problems for developers. Now, the ITripleE standard is supported by all major CPUs, which is great because it gives us a standard thing. We know how it's going to work. We know how it's going to be implemented. So that makes things a whole lot nicer for developers. Now, the floating point standard, something we want to keep in mind, is it was driven by numerical concerns. We've got nice standards for rounding, overflow, and underflow, but it's hard to make fast in hardware because numerical analysts kind of predominated over the hardware designers when the standard was being defined. So one example of something that kind of goes into that and came out of that process is we actually, in floating point, as we're going to see shortly, we actually have positive and negative values for 0. So I can actually have a positive 0 and a negative 0, which when we sort of think about it intuitively doesn't make a ton of sense, but that actually can be very useful in numerical analysis, which is well beyond our scope. But these are the kind of things. There are a few weird little things that we have to keep in mind. We just have to know that this is how it works. But, the reason that some of those came into the standard is because it wasn't necessarily just hardware folks. It wasn't just computer people putting this standard together. There was a lot of numerical analysis concerns that got into the standard, and that's a good thing. That's fine. It makes the standard more useful to more people, so that's great. But we just have to make sure that we understand how it all works so that we don't make mistakes because we don't know exactly what's going on when we start getting into the bits. So let's walk through a floating point representation and just sort of see what this all means. So we've got first -1 to the power of s. Now, what's s? S is our sign bit. It just determines whether the number is negative or positive. Okay, so the most significant bit, which you can see down here, this is just going to be a single bit. It's the most significant bit in the word that we have to work with. Remember, every time we're talking about one of these representations, this is going to fit into a word, some word size. So the most significant bit is our sign bit. Now, unlike with integers, that's not going to have any weight to it. It just indicates the sign of the value. So if it's a 1, then that's going to be a negative value. If it's a 0, then that's going to be a positive value. That's all this thing tells us. And we can see that from the math up here, right? -1 to the 1 is -1. -1 to the 0 is 1. So that just, again, all it's doing is indicating the sign of the value. Now, the significand, m, is normally going to be a fractional value in the range of 1.0 to 2.0. Now, we've got to pay attention when we're dealing with these mathematical notations here. All right, notice that this range, we have a little square bracket on the left and the rounded parenthesis on the right. That indicates that 1.0 is inclusive on that side of the range, but the 2.0 is exclusive. So the significand is going to be between 1.0 and whatever's just barely under 2.0, right? It's never actually going to be 2.0. And the exponent e weights the value by some power of 2. Okay, so when we look at these fields down here, we see actually we have some different names, and that can be a little confusing because what we're talking about in this mathematical representation on the top are the values. Okay, these are the sort of the mathematical values. This is what we're talking about in a more abstract way. When we look at the fields that would actually contain the bits, we're going to have the EXP field, which encodes E from the top, right? So EXP encodes the exponent, but it's not actually equal to the exponent, and we'll see why that is in a little bit. The frac field encodes the significand, but it's not equal to M. Okay, and there are good reasons. I know this seems a little weird and confusing, and like, why would we do it this way? Well, there are very good reasons to do it this way, and you'll see that as we get deeper and deeper into how these all work. But those are the things to keep in mind. Mathematically speaking, -1 to the s being the value of the sign bit, times the significand, times 2 to the exponent e, is going to be our value of our floating point number. The fields, again, EXP encodes E, but isn't the same thing as E. The frac field encodes M, but it's not equal to M. So let's try to sort of keep that in mind as we move forward, and we'll dive into why all those things are the case as we move through this video. So just sort of put a pin in those for the moment, keep it in mind, and we'll get into why all of these things are true as we move forward. Now, speaking of that word size that I mentioned on the last slide, we've got several different specific options based on the word size that we're using to represent floating point numbers. And they all have their specific names, and they all have specific numbers of bits that are given to each of these fields, so we want to make sure we're familiar with those. If we're talking about 32-bit words, that's called single precision floating point. We've got 1 bit for the sign bit, of course. We've got 8 bits in that case for the EXP field that's going to encode the value of E, and we've got 23 bits to work with for the frac field, which encodes the value of M. For double precision, we have 64 bits. Again, 1 bit for the sign. In this case, though, we're going to have 11 bits to encode E in the EXP field, and 52 bits for the frac field encoding M. Now, another one that's for Intel only, we might actually have extended precision, which allows for 80 bits, in which case, as always, 1 bit for the sign bit. We have 15 bits in the EXP field to encode the exponent, and 63 or 64 bits in the frac field to encode the significand. Now, we've got several different kinds of values that we can represent with our floating point notation. These are normalized values, which we'll talk about in detail in this slide, and then we'll also talk about something called denormalized values, and then there are several special values. Now, there's some good news here. First of all, they all work for the same mathematics as we used before to get the value, right? This -1 to the s times m times 2 to the e, that's going to work regardless. Now, it's also easy to figure out what kind of value we're using because there are just rules based on what the bits look like in the various fields that tell us what kind of value it is. So for normalized values, if the exponent, okay, so the bits in the EXP field are not 0 and they're not all 1s, right? So if they're all 1s in the EXP field, we're not in normalized. If they're all 0s in the EXP field, we're not looking at a normalized value. If it's neither one, then we know that we're looking at a normalized value. So it's pretty easy to determine what kind of value we're looking at. So let's dive into some of that stuff that I would promise to go through about why these fields don't necessarily just directly reflect the mathematical values we're talking about. So first of all, the exponents. The exponent is coded as a biased value, right? So E, our mathematical E, from that 2 to the E up in the math there, for the value is going to actually be equal to capital EXP, which is the unsigned value of the EXP field. So if we just take the bits that are in the EXP field and treat them like an unsigned integer, right? That's the value of EXP with a capital E there. And then we just subtract the bias, whatever that happens to be. And this just gives us a lot of the range that we need because we need small values, we want large values. This is kind of how we do that. We bias the exponent. So the bias we calculate as 2 to the k minus 1 minus 1, where k is just the number of the exponent bits. So the precision of floating point representation that we're dealing with tells us what the bias is. For single precision, the bias ends up evaluating to 127. Okay, so because 2 to the 8 minus 1, remember we have 8 bits for the EXP field in single precision floating point. That's 2 to the 7th minus 1, that evaluates to 127. With double precision, it's 1023. We have 11 bits in the EXP field in double precision. 2 to the 11 minus 1 is 2 to the 10th, that's 1024. Minus 1 is 1023. So it's nice and simple. We can also tell fairly easily that the potential values for EXP are between 1 and 254. Right? We can't have 0 because if it's all zeros, it's not normalized, and that's what we're talking about right now. This is for normalized values. We can't have 255 because that would be 8 ones. So we go 1 down from that, we have 254. Again, same thing works for double precision. We've got 11 bits to work with, right? So the EXP value can be anywhere between 1, because we can't have all zeros for a normalized value, and 2046, because all ones would be 2047. So that means that the possible values for E up in this mathematics that we do to figure out the value for a single precision can be between negative 126, which is 1 minus 127 is negative 126, and 254 minus 127, which evaluates to 127. That's the potential values for the exponent that we can represent in the EXP field. But we've got to keep in mind, we can't just go look at those bits and translate them to as if they're an unsigned integer and call it a day. We have to actually subtract that bias, and that's why it encodes the exponent value but doesn't just directly reflect it, because we're giving ourselves more range by adding that bias in, and in order to do that, we have to do a little math to figure out what those bits actually represent. Now, the significand is encoded with an implied leading 1 when we're talking about normalized values. So our value of m, when we're looking at the value here, is going to be 1 point the bits of the frac field. So this series of x's is just representing the bits that are in the frac field for whatever encoding we happen to be looking at. But we add that 1 point, that 1 to the left of the binary point doesn't actually have to show up in the encoding, so we save a bit, right? How cool is that? The whole idea behind floating point is to give ourselves a better range and to use our word size in a much more flexible way. So, hey, if we can save a bit, why waste it if we don't need it? If we know that if we're having a normalized value, the significand is going to be 1 dot and then the value, whatever bits are in the frac field. So it's minimum when frac is all zeros, right? That just means that our significand is going to be 1.0, right? If we take a 1 point, that's implied because we know we're using a normalized value. Tack on a whole bunch of zeros, that just means that our significand is 1.0. Now it's going to be maximum when frac is all ones. And we can also reflect that is, remember that epsilon notation we talked about? 2.0 minus epsilon. And that's why in the range that we talked about for the significand, we said it will approach 2 but never actually get there. If it's 1 dot a whole bunch of ones after the binary point, we start getting closer and closer to 2, but we don't actually get there. So it's still 1 point something, and the point something is variable. We're using epsilon because depending on the precision, single precision versus double precision versus extended precision, we have different numbers of bits in the frac field, which means we have different values for what that epsilon actually is. So again, for normalized, it's really cool. We get the leading bit for free. We don't have to waste a bit within our word to get that 1 point part of the significand. We can just assume that it's there because that's how the standard works. So let's take a look at an example of how to encode a normalized number. So let's say we have the value of a float is going to be 15,213.0. We should recognize this from back in the videos when we were going over integer encodings, right? We've used this example before. So if we take 15,213 decimal and just turn it into an unsigned integer, we get this bit pattern here. Now, we want to turn this into something of the form 1 point something, right? Because we're looking at a normalized value. And so we know we're going to have our significand is going to have that implied leading 1 and then the binary point and then what ends up in the frac field. So if we just assume that the binary point, of course, is over to the right in our unsigned integer representation, how many places would we have to move it to the left in order to get a something of the form 1 point whatever? Well, if we count this over, we find out that it's 13 places. So we can represent this unsigned integer as 1.1101101101101 times 2 to the 13th power. Because remember, when we multiply by 2 to some exponent, all we do is move the binary point to the right that many places. So we can represent 15,213 as 1, then the binary point, then the rest of this, times 2 to the 13th. Well, hey, that kind of looks like we're getting more into the form of a floating point number, doesn't it? So our significand, m, from the math up here in the top right, is going to be 1 dot, that thing we figured out, right? 1.1101101101101. That's our actual value of our significand. So our frac field, the bits of the frac field, are going to be that bit pattern that's to the right of the binary point, because remember, we get this leading 1 by default. We don't have to represent that. That's assumed. So we take that remaining bit pattern, and then let's just pad it over to the right with zeros, because we have to fill up. We have 23 bits of information in the frac field for a single precision. We've got to fill all of those up. So we'll take our bit pattern, pad it out with as many zeros as we need to get to 23 bits, and we have our frac field. Now let's deal with the EXP field. Now remember, this is a little weird, right? The mathematical value of E we know is 13, right? We figured that out up here. We know that our bias is going to be 127. How do we know that? Well, remember the bias is 2 to the k minus 1 minus 1, where k is the number of bits we have in our EXP field. For a single precision floating point, that's 8 bits. So 2 to the 8 minus 1 is 2 to the 7, which is 128. Subtract 1, we get 127. So we know what our bias is. Now we can look at this equation up here, E equals exp, or E equals EXP minus the bias. Do a little algebra. We find out that the value of EXP is going to be E plus the bias. So we add those up, we get 140. That's what is going to be directly encoded into the bits of the EXP field. So we just convert that to binary as though it's an unsigned integer again. And 140 ends up being 10001100. So we just fill in the EXP field with those bits. Now the sign field is super easy, right? The sign bit is just a single bit indicating whether this is negative or positive. We're representing a positive value, so the sign bit will be 0 because -1 to the 0 is 1. That's positive. If we were encoding negative 15,213, we would just make the sign bit 1 to indicate that this is a negative value. And so that's what it is. We have to do some investigation. We have to remember these relationships. So it's a little more complicated to go back and forth to floating point representations, but it's not really all that complicated, right? As long as we remember these relationships and we remember that, for example, for a normalized value, we have that implied leading 1 on our significand. All we have to do is remember the rules and apply them, and we can go back and forth between floating point bit representations and the actual values that they reflect. Now, don't worry, we're going to go through more examples of this later in the video so we can get plenty of practice and make sure that we really have a firm grasp on this. Okay, so we know what normalized values look like and how they behave, so let's take a look at denormalized values. Now, the condition for a denormalized value, we're going to know that we're dealing with a denormalized value if the EXP field is full of zeros. That's how we know it's a denormalized value. And things are a little bit different. We calculate the value in the same way, right? The math on that is the same. But for the exponent value, the capital E in the equation here, we actually do 1 minus the bias. If we just used the EXP field and calculated that capital EXP as if it was just an unsigned integer, it would be 0 minus bias. But when we're dealing with denormalized values, we actually do 1 minus the bias. So that's just something a rule that we want to keep in mind. Now, the significand is encoded with an implied leading 0 for denormalized. So that's another difference. Instead of an implied 1 dot whatever, we have an implied 0 dot whatever. And just like with denormalized, though, the x's here, or everything to the right of the binary point, is just the bits of the frac field. So there's a couple cases to keep in mind. If the EXP field is all zeros and the frac field is all zeros, that represents a 0 value, right? That's how we actually do 0 in floating point. But note that the sign bit still applies. So we have a positive 0 and a negative 0. Why? Well, again, that goes back to the numerical analysis concerns that were there in the room when the standard was being created. If the EXP field is all zeros and the frac field is not all zeros, this gives us those numbers closest to 0.0, right? This is where we're actually going to end up with that 1 minus epsilon, because with a denormalized value, we have that implied leading 0, so denormalized values are always going to be less than 1. They're going to be those purely fractional values as we get close to the zeros. Now, we also have some special values. Now, the condition for these, the way we know that we're dealing with one of these special cases, is if the EXP field is full of 1s. So if every bit in the EXP field are 1s, now we know that we're dealing with a special case. So the first one is if we have all 1s in the EXP field and all zeros in the frac field, we're going to be representing an infinity, right? An infinite value. And this is basically what happens when we have an operation that overflows. And this can be either, just like with zeros, we can have positive infinity and negative infinity. So positive 1.0 divided by positive 0.0 is the same as negative 1.0 divided by negative 0. And that's going to be a positive infinity. If we mix our signs, right, so if we try to divide 1 by negative 0, we get negative infinity. So once again, if we look at a floating point representation, we see that the EXP field is full of 1s, the frac field is full of zeros. We still have to look at that sign bit. The sign bit still matters because we do differentiate between positive and negative infinity. Now, if we have all 1s in the EXP field and we don't have all 1s in the frac field, this is the way we indicate not a number. This is a case, there is no numeric value that can be determined. So if we try to do an imaginary number, so the square root of -1, or we try to subtract infinity from infinity, or multiply infinity by something, this is going to evaluate to not a number. So let's kind of take a look at these on a number line to get an idea of where these ranges lie. We have our zeros. Remember, again, we have a -0 and a positive 0, and we have to keep track of which we're talking about. And then as we get away from the origin, we have our denormalized values, right? Because those are going to be less than 1. Our significand has an implied leading 0. So those are the ones that are closest to the zeros, to the origin of a number line. Then we move up into our normalized values, and finally we hit our infinities on either side. And then just sort of somewhere out there, we have our nada numbers, which is, again, what happens when we try to represent imaginary numbers or something along those lines. So now let's explore some properties of floating point numbers and how they're distributed by taking a look at a couple smaller representations. We'll actually do an 8-bit representation of a floating point number and a 6-bit representation of a floating point style number to get an idea of how these ranges end up arranging themselves and how they end up distributing themselves across the number line. So let's take a look at a tiny floating point example. Let's just do an 8-bit floating point representation where all the same rules actually apply. We'll use the sign bit will be the most significant bit. We'll go ahead and use 4 bits for the exponent, which gives it a bias of 7, because that works the same way, right? 2 to the k minus 1, where k is 4, is 2 to the 3, which is 8, minus 1, so our bias is 7. The last 3 bits will be the frac field, and this is going to use the same rules as the ITripleE format. It doesn't have to be, those standard precision or double precision like we talked about before. I mean, that's what we use in actual computers, but we can apply the same rules to whatever number of bits, whatever word size we want. So we're still going to have normalized and denormalized values, and we'll still have multiple representations of 0, not a number, and infinity. So we can, by using this smaller representation, we can take a look at the range, and this is just the positive values only, that we can represent, and we can see how these bit patterns work for us, how we recognize these things. So for our denormalized numbers at the top, we see, well, what's our rule? All of the exponent bits, all of the exp bits are 0. So we kind of move on through and we get up to 7 over 512, right? 7 512ths ends up being our largest denormalized value with this arrangement of fields. Now, keep in mind, again, that when we're doing this, if our significand is always less than 1, right? Because we have an implied leading 0 instead of implied leading 1, and that gets us up to 7 512ths. Now, from 8 512ths and up, we're into our normalized range. Now, note that when we talk about, in the previous slides, when I've talked about something in denormalized being less than 1, we're talking about the significand, right? Because we're multiplying by that 2 to the e and we can have a negative exponent, normalized numbers are not just from 1 and up, right? We can still have very, very small numbers in the normalized range. In this case, we're starting with 8 512ths, right? So as we move on up, we find that we just keep on counting, and eventually we get to the point that we're going to run out of the option to represent things without our exp field becoming all 1s. Now, when it does, we have all 1s in the exp field, and if we have all 0s in the frac field, now this is positive infinity. So that takes us through the entire positive range from a 0 special case where we have 0s in the exp and the frac field, all the way up through the denormalized, then through the normalized numbers, finally to the positive infinity. Another thing we want to note is the distribution of values. The distribution actually gets denser as we move toward 0. These points were generated from a 6-bit IEEE-like format where we've got 1 sign bit, 3 exp bits, and 2 frac bits. But again, that doesn't matter. It follows the same rules. And so we see that as we get higher and higher, and we're in the normalized range, it clusters a little bit more. It's dense, it's more densely packed as we get towards 0, and then things spread out as we get to higher, both positive and negative numbers. So I guess I should say larger positive and negative numbers. And then, of course, eventually we hit the point where we start getting into the infinite values on either end. If we take a closer look, we can see that actually in the denormalized range, they're going to be equidistant from each other. Then once we hit the normalized range, they start spreading out as we get to larger and larger values. And again, that works both in the positive and negative directions. Finally, there are some special properties of the IEEE encoding that we have to keep in mind because we don't want to do things too similarly to how we've done other things so far, like when we were dealing with integers. A floating point 0 is the same as an integer 0, right? All the bits are 0. That gives us a 0. We can almost use unsigned integer comparisons, but we've got to keep in mind we always have to compare those sign bits. We have to consider -0 and +0. Also, not a numbers are problematic. They're going to be greater than any other values, but what should a comparison yield? Well, a comparison shouldn't really yield anything because it's not a number, so we're not actually comparing two like things. So comparing 1 to a really huge not a number, we're still comparing a number to not a number, so that there is no comparison to be drawn. Otherwise, we're fine. Denormalized versus normalized, normalized versus infinity, all of our comparisons are going to work just fine for those ranges, but the 0s and the not a numbers are a little bit weird, and so we've got to keep in mind to check for not a number, make sure that we're not dealing with a not a number before we process it like it is a number, and make sure that we're keeping in mind that zeros have signs. And that does it for our basic introduction to floating point numbers. So what we want to take away from this is we need to be able to use fractional binary numbers. We have to explain what is the significand and what's the frac field, what's the exponent and what's the exp field, and keep in mind that those things do not directly map because we have the bias that we have to deal with. So we should be able to explain what that is and be able to calculate it given a particular floating point representation. And we want to differentiate between the various types of floating point numbers, like the denormalized and the normalized and those special values. We should know how to identify them and know the differences in how they work when we're encoding with them.